Natural disasters like earthquakes, storms, floods, etc. typically damages infrastructures, trap numerous individuals, and may result in a huge death toll. A prompt life-saving response is required to rescue those trapped under debris. In the recent years, the rescue agencies rely on the search and rescue robots. In a worst-affected disaster site, there can be communication failures and the path to the base station will be damaged with many obstacles. Therefore, the rescue teams cannot drive to the disaster site to deliver the robots and equipments to set up the base station. The only solution will be to teleoperate the robot or carry it on a team member's back. Robot platooning is a well-known method to handle robots in a disaster site. Robot Platoon has one leader robot and many followers. This project proposes a vision-based robot platooning algorithm that is capable of maneuvering teams of search and rescue robots around in a dynamic disaster sites under the assumption of no available communication network. The position information of the leader robot was detected by a Kinect camera. All the follower robots in the platoon subscribes to the depth information of the robot that is in front of it. The linear and angular velocities are controlled based on this depth info. A navigation algorithm named FISVFH has been used for navigating the leader to the desired location. The algorithm has been tested in different scenarios and the details of the tested scenarios will be demonstrated now. The test scenario that you see in the video has been set up in the engineering high bay. The site is 70 meters long and 20 meters wide. As you can see, the platoon consists a total of 5 robots, 3 Pioneer P3DX robots and 2 Jackal robots. 2 destination points were assigned to the platoon. First 2 robots were given a destination point A, which is 40 meters away from the starting location, and the second set of robots were assigned a destination B, which is 70 meters away from the starting point. The platoon, under the leadership of the first robot, takes all his followers to the assigned destination points by avoiding obstacles and following a safe path. The selection of 2 different types of robot is to prove that our platooning algorithm is capable to be implemented on any type of robots, whether they are either differential drive or skid steer. The platoon is still moving towards its first destination point. The doll at the base station represents an official from the agency. The first destination point to set up the base station is near the doll. Now the platoon has reached the first destination point. Once the platoon has reached the first destination, 2 robots will stay back there to serve that particular base station. The platoon is now divided into 2 after a switching time of 30 seconds, which was configured in the main program. The second set of robots now turns out as a new platoon set, and the robots with the leadership of the new leader robot starts to navigate to the second goal point. Like how you saw the robot avoiding the obstacles in the first part of the platoon, the same conventions are followed here too. The platoon avoids all the obstacles along the way, successfully maneuvering towards its destination. The second platoon has also reached its destination and the entire mission was successfully accomplished. As a conclusion, the platooning algorithm that is capable of maneuvering teams of robots in a potentially evolving disaster site under the assumption of no available communication network is developed and tested. During the experimentation phase, the algorithm showed enough robustness to adapt dynamically to the severely devastated environment and successfully drove the rest of the platoon to the desired destination. Thank you.